Okay, hey everybody. So today we're going to be talking about some of the components in a text generation pipeline that we haven't yet discussed, but which are pretty important if you're going to use any sort of language modeling to generate text. And as we saw last time with GPT-3, we can conceivably turn almost any NLP problem into a text generation problem by feeding in examples or a description of a task in as a prefix to a language model and having it generate text that kind of solves the task, right? So answers in a question answering system or translations in the target language for a machine translation system or so on. So it's important to know how we're going to decode and also evaluate the quality of our outputs, especially if we're trying to compare a model generated text to some ground truth reference text. Okay, so before we get into the topic, there's just one question from the anonymous forum from last time. Someone asked for more implementation heavy classes that are less, I guess, high level researchy. So I can plan to do one of these maybe sometime in the next couple of weeks where we, I don't know, implement a model or use something like BERT to solve a task. You will also be doing this in your upcoming homework. So maybe that will address this to some degree, but yeah, I do understand we're talking about a lot of pretty complicated models, and it'd be good to get some hands-on experience with them. So I'll try and incorporate some more coding stuff into my lectures, and also I think the homework will be helpful here. So just a tentative plan on the homework, we're just finishing that up. It will definitely be released this week. I know I've been saying that for the last like 5 weeks, but it is coming, and we're going to have it due like a week before the exam. So you'll have some time to just focus on the exam reviewing stuff. And then, yeah, we're also planning to kind of drop homework too. So we're not going to overload you in the last month of November. And give you more time to finish your final projects. I should also mention that your project feedback, we are finishing that up and it'll be released on Friday. So feedback on your project proposals. So homework 1 will be released also hopefully Friday, but definitely by the end of the weekend. And we'll give you 2, maybe 2.5 weeks to complete it. So hopefully that'll be enough time. Okay, as usual, feel free to ask additional questions in the chat box. So for most of this lecture, we'll focus on machine translation as the main example of a text generation task. When we talk about decoding from models and evaluating, machine translation is kind of the canonical text generation task. It's been around for many, many years, and it probably has the most value as a, an industry or even as a benefit to society, right? Google Translate used or other translate tools are used all over by many, many people, and neural networks have significantly improved their quality. So an important question to ask is, so we've covered how to train these models, right? We've talked about, training language models, training them in the sequence-to-sequence setting. Essentially, we are just computing the cross-entropy loss at the token level and averaging. So we've seen the training before, but we haven't actually completed the rest of the pipeline from what do we do at test time, how do we get a translation for a given input sentence, and then how do we know how good that translation is. So here in this Chinese to English example, we see the system's output is not very coherent, right? It says, the reporters learned that this ministry plans to build a separate city to solve the basic black water up to now, blah, blah, blah. These cities were identified to confirm the black and white water 2082. Like, this doesn't make any sense, right? You can see that it does match with some of the numbers that are in the input, but the actual meaning of this paragraph is very unlikely. I mean, it doesn't even make sense. So this is a bad translation. In general, Chinese to English, English to Chinese, this is a difficult translation pair compared to something like French to English, where there's far more training data, and also there's a lot more like just one-to-one mappings between French word and English word. With Chinese, you have to deal with the big character set and so on. But here you can see, I mean, I don't know French, obviously. I think all the examples I've had in this class have been French, and yeah, I clearly don't understand them. But if you read the English translation here, you can see that it's quite fluent. It's completely grammatical and makes sense compared to this Chinese to English translation here. So I have a question. Wait, so the training loss is not the metric we use for evaluation? No. So we don't use a training loss for evaluation. Remember, to evaluate all models, not just text generation models, we have some held out data, right? So in the case of translation, we'll have some set of sentences that we have not observed at training time. And we're not going to just evaluate our model's performance by measuring the loss of the ground truth translation or the probability of the ground truth translation. We're instead going to actually decode or generate tokens in the target language from our trained model, and then we're going to assume that we have access to some reference translation. So maybe in this case, like I have the ground truth translation in English as to what this Chinese paragraph translates into, and then I'm going to have some metrics that compare the text that I've generated from my model to the ground truth text. So that's how we're going to evaluate in this setting. And so for machine translation, kind of motivating this line of evaluation, you really want to measure the quality of text that the model generates. And so you have to take into account the decoding process, not just the loss or the probability assigned to the ground truth. So in machine translation, there are several different use cases that each of them can tolerate different levels of output quality. So in assimilation, this use case, the reader wants to know what the content is of some text that's in a foreign language. So they may not necessarily care of getting a perfect translation, right? Or even something that's grammatically correct for them. They might just want to know like what topics are covered in this source sentence or source document. And so the users here are pretty tolerant of getting translations that are low quality, as long as they get the general gist of things. The other use cases are, of course, communication. So maybe you're talking to someone who speaks a different language and you want to use a translation software to understand what they're saying and also communicate back to that person. So here, of course, quality is more important. Even if you make some grammatical errors that can really reduce the ability for your conversational partner to understand what you're saying. And finally, if you're talking about, like a publisher who wants to translate some content into multiple different languages and then make that available like publicly or for purchase or whatever, you of course need an incredibly high quality of output translation, right? So so much so that this task is not done by machines, right? It's done by human translators, and in some cases, translating, especially in like fiction, if I want to translate like, I don't know, Crime and Punishment, translation itself is kind of an art, just like writing the original story. So that is kind of far beyond the machine translation systems at this point. But just some idea of, for different use cases of machine translation, we might be tolerant of different levels of quality. Okay, so again, we're using translation here as an example of a text generation task, and we already went over this before, but remember in neural machine translation, our goal is given some French is our example, given some sentences in an input language, and we want to translate it into a different language. Our real goal here is to compute the sequence in the target language of words that has the maximum probability with respect to the input, right? So we're trying to maximize this conditional probability of E, which is in this example an English sentence, given the French input sentence. And also remember from the first few lectures that we're using our neural networks to directly model this probability by decomposing it into this product of conditional probabilities using the chain rule. So all pretty standard stuff. And we've talked about translation as an instance of a sequence-to-sequence learning problem where we could have two different neural networks to one model the French side, the input, the encoder, and the other to actually produce the tokens in the English or target language. And so we've looked at a couple of different cases of this, right? We've looked at the RNN to RNN, the RNN to RNN with attention, and finally the transformer to transformer, which is the predominant approach nowadays. So we've talked about training. Again, let's switch over to test time usage. So how do we actually get some text out of these models at test time that we can then design some metrics to evaluate them? So this process is called decoding. Given that we have a trained sequence-to-sequence model or even some sort of language model, in the case of translation, our goal is to compute this argmax, right? Is to find the English sentence that has the maximum probability given the input French sentence. And so one way you might think about doing this is to just enumerate every possible English sentence that I can construct, and then evaluate the probability of each of them under this translation model and pick the one with the highest probability. But of course, this is not feasible, right? First of all, I have probably a huge vocabulary of tens of thousands of tokens. I don't know what the length of this translation is going to be, and enumerating all possible English sequences is just going to be intractable. So this method doesn't work. The search space is too huge, and so we need to switch over to some sort of approximate methods of finding something that is highly probable, but maybe not necessarily the most probable English sentence. And so I think we discussed this or something similar to this before, but the easiest thing to do is greedy decoding. And so here, in this figure, I've only shown the decoder part of the sequence-to-sequence model. You can assume there's some encoder over here that's being fed in here. But the English translation is the poor don't have any money. So remember that we proceed word by word. We produce one word at a time. And for each word, for each input, remember we start with the start token. We're going to compute our recurrent hidden state in this example, or our transformer hidden state, or whatever. And finally, we get a probability distribution over all of the predicted next words, right, over the entire vocabulary. So here, in greedy decoding, I'm just going to take the word that has the max probability in this predicted distribution, and I'm going to produce that word. And so then I'm going to feed that word in as the next time step to my decoder, and I'm going to do the same thing. I'm going to compute a new hidden state. I'm going to compute a prediction over the next word, and I'm going to take the max probable word as my the word that I'm actually producing. So here I produced poor, then I go in, I do the same thing again, I take the max probable word, which is don't, and so on. And I stop decoding when I get to this end of sequence token, right? That indicates that I have completed the translation. So there's some issues with this approach, right? First of all, if I make a mistake early on, I don't really have a chance to go back and fix it. And it's it's not guaranteed that the word that I picked at the beginning is going to be correct. If I make a poor decision, that could really impact the rest of the words that I predict. So we might want a method that allows us to explore more possibilities than just this single argmax at each step. And so that's where beam search comes in. So if we want a method that allows us at least some capability of revising the decisions that we've made in the past, beam search is intuitively just allows us to explore several different translations instead of just a single one. So in the greedy decoding case, I only have a single candidate translation and I'm adding a new word to it at every time step, right? But the intuition behind beam search is, well, maybe I keep a couple of different candidate translations in mind, and I'm going to add words to each of these translations. And at some point, I'm going to prune translations that have lower probability to make room for candidates that have higher probability. So yeah, the intuition behind beam search is, instead of just taking the argmax at every step, we're going to keep track of a small number, k, most probable partial translations instead of just one. And so it's usually, between 5 and 10 maybe, but it kind of depends on your model size, your training data size, and also your task. This could differ a lot between like translation and something like summarization or story generation or something like that. So let's walk through how beam search works. And so in this example, we're going to say that our beam size is 2. So at each step here, you can think about this as corresponding to one time step of this decoder network. So at the start, I receive the start token at input. And remember, now I compute my hidden state. And I compute, using the softmax layer, a distribution over my target words. So with my beam size of 2, at this first step, I'm going to just take the 2 most probable words, given the start token, and also, of course, the encoder's representation. And I'm going to put them in as my 2 candidate translations. So I have one sentence that starts with the, and one sentence that starts with a. So these are my 2 candidates at this point. So here we're showing the log probability. Okay, so then I'm going to decode both of these paths. So I'm basically going to, for the next time step, look at the continuations for the, start the and start and I get a predicted probability distribution for each one of these, and I'm going to take for each one, look at the probable words. And to keep my beam size 2, I'm going to prune these candidates here. So I'm going to take the 2 candidates that have the highest log probability here. So that would be poor and poor. So my 2 candidates are now the poor and a poor. A question, are the values a log likelihood of the words? Yes, these are the logs, not the raw probabilities, of course. Now I have these 2 candidates, the poor and a poor. I'm just going to do the same process. I'm going to look at the predictions for the poor and a poor. I'm going to take the most probable words here. I'm going to get the poor are, the poor don't, a poor person, a poor but. So a poor but is clearly bad. And now I'm going to re-rank these based on their probability and take the 2 most probable ones. And so this time, they both come from this top branch, the poor are and the poor don't. So we're no longer considering any path that comes from this lower branch. This has all been pruned out and it won't be explored further. So now the only sequences that we're exploring are start the poor are and start the poor don't. So again, we get these 2 probabilities, these we get the output of the softmax layers for these two sequences, and we are going to do the same process, and so on until eventually we come up with the final most probable translation that we get out of this beam search. So it's very intuitive, it's simple to implement, and for translation at least, it results in higher quality outputs compared to greedy search, but there are some limitations of beam search. So first of all, we should consider, does it always produce the best translation? Like, does it compute the argmax? So usually I allow students to come up with answers to these questions, but in this case, I'm not. Okay, so before we get into that, there's a question. Why did we stop considering the lower branch? So I was referring to the lower branch as anything starting with the word and you can see that at this particular stage in this example, the two most probable candidate translations are both from this first branch, the poor R and the poor don't. Right, you can look at these log probabilities, and if you see here, the two candidates on the bottom side, a poor person and a poor but, both have lower probabilities. So in beam search, at every stage of the process, I'm going to prune the candidates back down to the beam size. So I always want to have a beam size of 2, meaning I have 2 candidate translations that I'm considering. So at this point, when I re-rank all of these probabilities, I find that these 2 are the highest. And so since my beam size is 2, I no longer consider these. I drop them off my beam, and I only expand the 2 most probable candidates that I have. So that's why we only expand here, and these ones we no longer consider because they were pruned off at this stage, as they weren't as probable as these 2. Hopefully that makes sense. Okay, so back to this question, does beam search always find the argmax? No, this is a search algorithm, right? It's an approximate search, and the search space is huge. We're not considering all possible things. It could be very possible that some translation that started with a poor person later on ended up being the most probable translation after you decode, like, I don't know, 50 more words. But since we pruned it at this this stage here, we're no longer considering any translations that start with a poor person, and so we're not going to be able to get that translation if it does turn out to be the most probable after some more decoding steps. That said, it is a compromise, right, between the greedy search, which only considers one candidate sequence, and the exhaustive search, which enumerates all possible sequences, right? At least here, we're looking at a couple of different candidates, even if it's still approximating the most probable translation. And in practice, it works pretty well. Okay, so what are the termination conditions of the beam search, right? How do we know when to terminate this process? So first of all, we're going to terminate any candidate translation when we reach the end of sequence token. Once we reach the end of sequence token, of course, we don't want to continue decoding more tokens, right? So then if there's still some other candidate that has we haven't produced the end of sequence token for that candidate, but we have for another candidate, we're going to continue expanding the candidate that has not completed yet. And we're going to prune things, but always keep the completed translation, the one that has terminated, on the beam, unless something we found is more probable than that one, in which case it could be pruned. So yeah, the beam search terminates once all of the candidate translations have terminated with the end of sequence symbol. Okay, is there a probability to get equal probabilities for 2 predictions? And if yes, then how do we go on to choose one of them? That's pretty rare in the case where you have such a huge vocabulary. I would say it's incredibly rare. It almost never happens in practice. But maybe it could happen in some more synthetic examples. If that happens, you probably would just choose one at random. So that's not something that you actually need to implement in your code. If you're implementing a beam search, it's not a practical issue. Is the log likelihood for the next word just the log likelihood for the next word? Oh yeah, that's a great question. Sorry, I should have mentioned. Yeah, it's a cumulative. So this is the probability for the entire candidate translation. And so this process makes it such that beam search is kind of biased towards shorter sequences, right? Because of course you can imagine if you expand with the chain rule, right, I'm multiplying probabilities with each other. So we would expect on average longer sentences to have lower probabilities than shorter ones. So there have been some methods proposed to like normalize for length and stuff in beam search, but in general that is something to keep in mind. Okay, and right, the next question has been answered. Right, because it is cumulative. Okay, so this third thing that I wanted to discuss, and this kind of segues into the next topic, is in translation, our goal is to find the most probable candidate translation, right? But in other applications of text generation, we might not necessarily want the absolute most probable output. We might actually want to maximize the diversity of our outputs, and we might be fine with something that has a relatively lower probability but has some, you know, interesting words or syntactic structures or something like that. So if you imagine a creative text generation task like story generation, for instance, then it maybe doesn't make sense to decode for the most probable word or sequence, but rather you might want something that you know, is interesting or enjoyable. And so there is a different class of decoding algorithms that are proposed for this kind of task, so not really relevant for translation. So maybe I'll come back to this and go to that. And this is just sampling-based decoding. So here we're not doing beam search. Instead, we are, and we're doing something that's closer to greedy search in that we have just one candidate. But instead of always taking the argmax probability of the next word, we're going to sample from the predicted distribution. So, you know, if my vocabulary is 50,000 tokens, if I go back to my greedy search figure here, so in greedy search, I'm taking the argmax of the distribution. But in a sampling-based approach, I could sample from the distribution instead. So if I do this, I'm not always going to predict the most probable word, right? And it's very likely that most of the probability mass is concentrated on other words that are like the rest of the vocabulary. So I might have a good chance of sampling a word that's not the. Similarly, I might sample something that's not poor, and so on. So since this is less constrained, and I could end up sampling an incredibly low probability translation if by random chance I sample some low probability word early on. Sampling-based approaches are not useful for machine translation. However, there are some ways that you can modify these sampling strategies to make them kind of produce things that are probable but also diverse. And so that's where we get this top N sampling. In the literature, it's called top K sampling, but since we already use K for beam search, we're going to call it top N sampling here. And this is kind of a hacky approach to modify this purely sampling-based strategy where at every time step, I'm going to compute my softmax over the vocabulary, then take the, let's say, 10 most probable words at a particular time step and sample from those. So in this case, I am guaranteed to be using like some of the most probable words at every time step, but I still have like more freedom in what I can produce. And so you can imagine that if I set n to 1 here, this is equivalent to greedy search. I'm always sampling the most probable word. And if I set n to the size of the vocabulary, then this becomes the same as just the pure sampling approach. So if you increase the value of n, so you're sampling for more things at each time step, then you're going to get way more diversity, but at the cost of possibly getting less probable outputs, which could be completely irrelevant to what you want to generate. And so this is the danger with translation, where you really want to be faithful to the meaning of the input. So increasing this diversity is too risky. And in contrast, if you go to something like greedy search, you're going to get more generic outputs. So that takes me back to the effect of beam size, because again, in beam search, if you think of a beam size of 1, that's equivalent to the greedy decoding that we've talked about. And practically speaking, if you decode from models using greedy decoding, you tend to get ungrammatical and nonsensical continuations. These are kind of artifacts of the modeling process. And some of the issues that people have noticed with greedy decoding include repetition. So the model tends to repeat things that it's already produced over and over and over again. There's some interesting papers on why this happens, and also a very interesting recent paper on the amount of probability mass that is assigned to non-terminating sequences. So sequences that just the model repeats and repeats and repeats over and over again without ever producing an end of sequence token, and sequences that actually terminate. So if you're interested in that, I'll put a link to that in the on the webpage after this. So the intuition behind beam search is that by considering more candidate translations, we're reducing the incidence of some of these issues with greedy search. Of course, it's more computationally expensive to do beam search. Now you have to evaluate these multiple probabilities, one for each of the candidate translations. And there's also some other issues that are kind of interesting with beam search. So you might imagine that increasing the value of k, the beam size, is always going to benefit me, right? Because I'm going to try as many possible translations as I can computationally handle. This will let me get the highest probability output. But this doesn't work out in either machine translation or in these more creative text generation tasks. So in machine translation, there have been several papers that show that if you, at some point, if you increase your beam size too much, the BLEU score, which we're going to talk about later, the measure that we have of translation quality, decreases. And a lot of this is due to the bias of beam search to favor short translations. And it's kind of hard to get rid of that even with some sort of length normalization. On the more creative generation tasks, if you increase your beam size, your output becomes more and more generic. So as an example of that, here are some responses in a chatbot using different beam sizes. So in a chatbot setting, your inputs are just like what someone has, like some user has written into the chat box. Yeah, whatever. And your sequence to sequence model takes as input the user's utterance and outputs something conditioned on that. So obviously a much less constrained task than machine translation. So here we have this human who said, I mostly eat a fresh and raw diet, so I save on groceries. And then we have a model that's trying to respond to that. So you can see that the greedy decoding, right, beam size of 1 says, I love to eat healthy and eat healthy. So this is, you know, I mean, it's obviously repeating itself. It loves to eat healthy twice. Raw food. I don't know why a nurse can't eat raw food, but at least it's still like kind of on topic. But then things kind of devolve here. So with beam size of 4, I am a nurse, so I'm a nurse. I mean, no one would say this in response to this input. And you can see that as I increase the beam size, I get more grammatical and less repetition, but I kind of diverge from the topic. So do you have any hobbies? Just ignoring this input. What do you do for a living? And so on. So this is a known phenomenon with these kinds of open-ended generation problems. We really don't like using beam search for these tasks and prefer the sampling-based approaches. So let's take a look at some of the sampling-based outputs. So these examples here are from a recent paper that came out earlier this year, which is proposing a new sampling strategy. I hope you guys can read this all right, but essentially there's a prompt. An unprecedented number of mostly young whales have become stranded on the West Australian coast since 2008. And so the examples in the previous slide were from an older model, like maybe 1 or 2 years ago. These examples were generated from GPT-2, so not GPT-3, but still like a very strong language model. And we're just going to look at a bunch of generations using different decoding strategies. So with a beam search of beam size 16, the model generates the number of stranded whales has increased by more than 50% in the past year, with the number of stranded whales on the West Australian coast increasing by more than 50% in the past year. The number of whales. So you can see that and the text highlighted in blue here indicates repetition of the model. So the model is just repeating something over and over and over again, and it hasn't terminated. So this is not what we want in this case. So in contrast, we can look at the pure sampling strategy, which remember, we are just sampling from the predicted distribution with no constraints on how many, like, are we sampling from the top n most probable or not. So in this case, we're just sampling from the top V, where V is the size of the vocabulary. It says the Australian Food Safety Authority has warned Australia's beaches may be revitalized this year because healthy seabirds and seals have been on the move. More than 50,000 seabirds, sea mammals, and seahorses have been swept into the sea by the Holden CS118 in the Adelaide airport from 2030. And Dauda migration across Australia is under. So this has nothing to do with young whales, right? And it quickly becomes incoherent, like an airport somehow sweeping animals into the sea. This is also not great. So now we can look at top N sampling, here top K, which again is a more common strategy. And here are two different values of K. So we see K equals 640, which is very large. And it's not great. It says pumping station number 3 shut down due to construction damage. It outputs a URL. And then it has something to do with whales. So, you know, it seems to be a little better maybe than the sampling strategy, but it's still not great. When you reduce the value of K to 40, you get something that's at least more related to whales. The whale's fate was confirmed late last week when the animal was found by fishermen off the coast of Bundaberg. Experts believe the whale was struck by a fishing vessel and died after being sucked into the ocean. And then we have it repeated again. But this one is probably the best one that we've seen. Well, maybe compared to the beam search one, I don't know. It still has problems. And finally, the approach proposed in this paper is kind of a variant of top K sampling, where you, instead of selecting a fixed number of words to sample from, like here 640 or 40, you instead select the n most probable words such that they form, say, 95% of the probability mass. So you're selecting a different number of words for each time step in this approach, which is called nucleus sampling or top P sampling. And you can see that the output here, there has been an unprecedented number of calves caught in the nets of whaling stations that operates in Western Australia, I guess, WA, blah, blah, blah. There's still some issues here. You can see the red highlighted text. Those are not about whales anymore. They're talking about like a fowl. So none of these methods is perfect, but with clever tuning of these sampling-based strategies, you can get pretty high-quality text out of these models. So this is something to consider for any of you who are experimenting with language generation models or language models in your projects. The decoding strategy is often just as important as the training process. Okay, so I see some questions here. Let's take them. So if we have a beam search with k equals 2 and 1 terminates, do we set k equals 1 from then on? Yeah, I kind of, so no, you don't do this. You're always going to expand. So you're going to consider, like in your other beam, you could potentially get 2 candidate translations that have higher probability than the one that's terminated. So you'd pop the one that terminated off the beam and continue with beam size of 2. So you don't just switch over to greedy decoding. Okay, so next question. Seems like the top-end strategy could pull in some branches with very different probabilities. Do people also sample the top-end most probable branches, but constrained within a certain probability difference? Yeah, so I think this is kind of related to the nucleus sampling approach that I just described, where well, not really. So yeah, I agree that like if one word is extremely probable and the second to 10th word are very low probability, then it's not great if you get a sample that of course samples one of those very low probability words. I'll say in general that that tends not to happen too much. Mostly these probabilities are kind of well distributed across a bunch of synonymous words. And in the case where there is one word that is, you know, obviously the next word, it gets a very, very high probability. So in nucleus sampling, we kind of address this because if there's one word that has, you know, 99% of the probability mass, we're only going to just sample that word. But in a case if, you know, there's like 10 different words that each have like 0.05 probability or something, then we're going to consider all of those. So yeah, nucleus sampling is probably the way to go if you want to address this problem. And that's if you want to learn more about that, you can read the paper that's linked on the bottom of this slide. Is there any ideal beam size value? What factors does a beam size depend on? Does it vary with the change in task? There's no ideal value. It's an empirical question. You have to try out a bunch of different beam sizes on your own task. It does definitely vary with your task and also with your specific data set. So you could have a translation data set that even in the same language direction, like maybe French to English, where one data set, maybe it's bigger or it has longer sentences or something like that, requires a larger beam size than another one. So yeah, it's kind of something you have to tune. How would this generalize to different kinds of text, say fiction or scientific papers? Yeah, so in scientific writing or any writing where you need to produce facts, you probably want to be a little more strict on any sort of sampling strategy that you're using. So if I'm doing like pure sampling, right, I'm likely to produce a lot of incoherent or just nonsensical facts like this airport and this random number or whatever Holden CS118 is. But in fiction, you know, maybe that's fine. As long as the text is coherent in general and grammatically correct and kind of relevant, that could be okay. We'll talk more next week about long-form text generation and the issues there with maintaining coherence and stuff like that. But yeah, it's kind of hard to say. I would say that the decoding approach definitely should be considered as like you should pick based on your task, but I can't really suggest anything more than trial and error here, and I think that's what people in general do. So finally, a question about this task on this slide. This is just a language modeling task. So the prefix here is this bolded text, and these are just the next words that the model predicts. So similar to what we saw in the last class, it's just a simple language model where we've seeded it with some content in the prefix. Okay, great. So just to summarize, probably never want to use greedy decoding. It's very rarely going to give you the best quality outputs. Beam search is good for tasks like translation or maybe more domain-specific tasks where it's very important to produce things with high probability. And sampling methods are better for creative tasks or things that are more open-ended, like chatbots or poetry generation or something like that. And even within the sampling methods, there are variants that allow you to kind of bias the outputs towards things that are more probable by using top K sampling, etc. All right, so that's all I wanted to say about decoding. Now I want to get to evaluation. So we're going to focus mainly on translation as an example, but the metric that we're going to talk about here is used very commonly for many other text generation tasks, even in cases where it shouldn't be. So the problem with translation, and more broadly with more other text generation problems, is that there's no one right answer, right? So in this example, I'm not sure exactly what this Chinese sentence says, but there are multiple candidate translations in English. Israeli officials are responsible for airport security. Israel is in charge of security at this airport, right? There's many paraphrases of this initial translation that could be acceptable in this case. And my model is going to produce one of these using whatever strategy that I am using, right? Beam search or greedy decoding or whatever. So should I really be penalizing it for producing, say, one of these and not another? And more generally, how do I know like whether my translation that my model produced is good or not? So there are two basic ways in which we want to evaluate the outputs of a translation system and also other text generation tasks, and these are on adequacy and fluency. So adequacy measures essentially, does the output in machine translation have the same meaning as the input sentence, right? So if parts of the sentence, the semantics were dropped, or some new information was hallucinated, we want to give it a low score on adequacy. The second dimension is fluency, right? So is the output grammatical? Does it look natural? And yeah, so that's also, of course, important. So a translation could be adequate without being fluent, right? It could have some minor syntactic issues, but for a human reader, it could be fine. You can still make out the meaning, even though there's some issues with the, again. Okay, it said I disconnected and has now been reconnected. Hopefully that wasn't a big interruption to you all. So as I was saying, the other dimension here is fluency, and you can have a perfectly fluent generated output that has nothing to do with the source sentence, right? So this would be bad, and we would want our adequacy score to be low in this case. Okay, so one way you could think about doing this is performing a human evaluation. So in a human evaluation, you would have translators who are maybe familiar with both languages and ask them to evaluate the model-generated text on both of these dimensions using some sort of scale, right? So these are some examples from 1 to 5, rate how adequate the text is and how fluent it is. And so you can, devise some interface like this in which humans can rate candidate translations. Especially, you can make it easier for them by giving them a reference translation. So yeah, at this point, I would allow you all to vote on these translations, but let's just go through some of them. So we have this French source sentence, and the ground truth translation here, the reference is there not an element of hypocrisy on your part? And so we have three system outputs here. System one, would it not as a wave of hypocrisy on your part? So this seems not very fluent and maybe also not adequate. Like a wave of hypocrisy doesn't seem to be conveying the same meaning, although you can probably roughly tell what the meaning here is. So maybe I'd give this like a 3 or 4 on adequacy. System 2 is there would be no hypocrisy, like a wave of your hand. This one, it doesn't seem adequate at all. A wave of your hand was just inserted in here, and it's also not fluent. Is there would be is obviously ungrammatical. And is there not as a wave of hypocrisy from you? So like these would be examples where you know, this is a subjective task, right? What does it mean to be 3 on this adequacy scale as opposed to 4? So you would want to have a lot of raters and compute their, you know, agreement or average score or something like that. Of course, there are many issues with human evaluation of generated text. In addition to it being subjective, it's also very expensive, right? So I can't actually expect my human evaluators to evaluate like millions of model outputs. I don't want something that takes up a lot of time as well. So I want ideally some score that is cheap and free and has the least time investment possible for me to decide how well my model is doing. And that's why we kind of turn to automatic evaluation metrics. So here we have some sort of automatic computerized way of evaluating the quality of a generated text. And one way you could think about doing this is just simply calculating the precision and recall when compared to some reference sentence. So here, if my system produced Israeli officials' responsibility of airport safety, and the ground truth translation was Israeli officials are responsible for airport security, I could just look at word level overlap, right? So in my system output, I see Israeli officials and airport are all words that occur in the candidate translation. So when I compute my precision, I get 50% precision because these 3 words were not present in the reference. I can compute my recall, so how many words in the generated text how many words in the reference were present in the generated text. And then I can do some aggregate of these, compute the F-score to get some idea of how my model is doing. But this is not a great way of evaluating these translations, right? Because it doesn't consider the order of the words at all. And so that might be bad if I'm interested in also measuring fluency, right? So as an example of this, I have 2 system outputs here: Israeli officials' responsibility of airport safety, and also airport security. Israeli officials are responsible. So I think here we would like to say that, I mean, it's a little unclear which one of these is better, but if you use the metrics that we've defined here, which simple precision and recall of the words, system A is scored much lower than system B, and system B actually achieves 100% F measure on this task. And that's not good, right? Because system B is not generating a fluent piece of text. It actually generates this fragment, airport security, period, and then Israeli officials are responsible. So, oh, that's not a period. Anyway, this is not a grammatical sentence, and there's no way this should be getting 100%. So this issue kind of motivates the metric that is most commonly used in machine translation, which is the BLEU score. And so BLEU stands for Bilingual Evaluation Understudy. It is very similar conceptually to what we just described, except we're going to be calculating the precision of n-grams, not just unigrams or single word. So the idea is that if I'm considering n-grams from size 1 to 4, like a 4-gram, to have a matching 4-gram, that means that at least some local syntax is matched here. And so I get some representation of fluency beyond what I get from just single word matching. Okay, so in the BLEU score, we don't actually explicitly encode the recall. So if you remember here, we computed the recall of these words. Here, we're going to add this brevity penalty instead, which is going to penalize translations that are too short. So we're going to take this geometric average of the n-gram precision going from 1 to 4. That's described here. And then we're going to multiply it by this brevity penalty as well. That penalizes translations that are too short. And so one question you might have is, why do we do this brevity penalty thing instead of just computing the recall and then using the F score as our measure? And the reason is that BLEU was designed to work with multiple reference translations. So as we mentioned before, there's not just one single translation that is like the best one, and no other translation is adequate. There's actually several adequate paraphrases of a single translation. So if you have a data set with multiple references, so in this case here, I have 4 different reference sentences for this translation, I can actually compute my precision using all of these references, right? So here I see Israeli officials is matched in this first sentence, so I get a bigram match that counts for my BLEU score. This bigram responsibility of was matched in the third reference, I get some points for that. An airport was matched here. Unfortunately, I don't have any 4-gram matches, right? Israeli official responsibility of, that doesn't occur in any of these references, so I don't get points for that. Yeah, if you look at the precision here of these different n-grams, you see that system A here, this one gets 0 because there's no matching 4 grams, right? So I didn't actually get to match any of the Israeli officials' responsibility of, or officials' responsibility of airport, or responsibility of airport safety. None of these were matched in my references. So I don't include them. I get 0 points for 4-gram precision, and as such, I have a 0% BLEU score. System B, on the other hand, actually does contain a 4-gram match. Israeli officials responsible. You can see that here, Israeli officials are responsible occurs in the first reference. And so it gets a BLEU score, but remember that our previous metric here was giving it 100%. And we see that the BLEU for this sentence generated by system B is 52. So it's saying that this translation is not perfect, right? It still has some flaws, which, as we can see, it clearly does. So recall in this setting is hard to compute because we have multiple references, right? So it's there's a lot of wind. It's a little unfair of us to ask the model to match every single n-gram that occurs in every single reference, right? That's unfair. We only have a single translation, so it doesn't make sense to include recall as part of this computation. Okay, great. So that's BLEU, and one of the downsides of BLEU is that it treats all words and n-grams as equally relevant and meaningful, when certain n-grams or certain words might be much more semantically informative than others. So this is one issue. And another thing is it's still operating on this local level. So the biggest contiguous, I don't know if you guys can, wow. Okay, it's just like a hailstorm. I may lose power, I don't know. Okay, I guess I will wait until this stops for continuing. All right, that was crazy. Back to BLEU score. So as I was saying, the what was I saying? Right, we're only looking at the max of a 4-gram here, so we're not considering like the global sentence coherence in BLEU. And human translators also score fairly low on BLEU, which indicates that maybe it's not perfect. All right, so some questions. Why are part of speech tags not a part of these metrics, or are there any that do include part of speech tags? It's not clear that part of speech tags are a useful way of evaluating the generated text. I'm not sure how you would incorporate that into something like translation quality. Right, what would you use it for? Has the model generated the right number of nouns and verbs? Maybe that could be a reasonable thing, but in general, you care more about the actual words themselves that the model is producing, right? For example, here, if I produced like submarine instead of airport, I would get the same part of speech tag, but the meaning is completely different. So yeah, in general, we don't incorporate part of speech into these evaluations. And Andy asked, do you usually have parallel data with multiple references? Yeah, sadly, no, you don't. BLEU was designed for this ideal setting, but most translation data sets have just a single reference translation. And in other tasks like story generation or whatever, you have also just a single, or like chitchat, you have a single reference. So yeah, it's really designed for multiple references, but we normally use it with just a single reference. So yeah, it has many flaws, but people have shown that it does correlate with human judgments, which is why people still use BLEU. It's also very, very easy to implement. There's standard packages that you can use to measure BLEU score. So yeah, overall, it's a good thing to do. Okay, so just to conclude really quick here, I don't know for how much longer I'll have power the way this is going. One thing that more recently people have been looking into is trying to get some of our more fancy models like BERT and these other huge scale language models into the evaluation process, right? Because we know that these models have, if not, they don't understand language, obviously, but they certainly are doing something that's more complex than simple n-gram matching or word matching,